October 3rd, 2025. 6 spacecraft orbiting Mars are capturing the closest views ever of an interstellar object. 3I/Atlas, a colossal 20-kilometer traveler passing 9 times nearer to us than Earth's telescopes could ever hope for. In less than 72 hours, it will vanish behind the sun, possibly forever. Just 3 interstellar visitors have ever been confirmed. One the length of a skyscraper, one slightly larger, and now this. An odds-defying giant, no survey expected. NASA has confirmed. Mars is suddenly the front-row seat for a cosmic event that rewrites what we thought was possible. But as data floods in, the numbers threaten to overturn every model. The real mystery begins as the comet prepares to disappear. 3 interstellar objects in less than a decade, each one rewriting the odds. Astronomers expected to find a steady parade of small, dim wanderers, fragments barely the size of a city block. Instead, the universe dealt a statistical outlier. The first, Oumuamua, measured just 400 meters across, already a surprise, given the vastness of interstellar space and the limitations of our surveys. 2 years later, Borisov appeared, a kilometer-long comet with a tail of dust and gas, confirming that the first was no fluke. But then came Atlas, 20 kilometers end to end, dwarfing its predecessors by orders of magnitude. If survey models held true, the chance of finding a giant like this before thousands of smaller ones was less than 1 in 10,000. Yet here it was, on a trajectory that would bring it closer to Mars than any interstellar object has ever come to a planet with a waiting fleet. Statistical models built from decades of comet and asteroid tracking predicted that the vast majority of interstellar visitors would be small, faint, and nearly impossible to detect. Large bodies, those with enough mass to survive ejection from their home systems, should be scattered thinly across the galaxy, their numbers dwarfed by the countless pebbles and shards too dim for even our best telescopes. Survey teams have spent years refining detection algorithms, accounting for every bias, every patch of sky left unscanned. And still, the numbers didn't add up. The odds of finding a 20-kilometer traveler first, before a parade of smaller, more typical debris, defied every expectation. Atlas is a cosmic jackpot, a statistical anomaly that calls the entire model into question. The Mars encounter amplifies the improbability, not just the size but the timing and geometry. 6 orbiters, each equipped with cameras and spectrometers designed for Mars, suddenly repurposed for a once-in-history chase. Mars Express, with its 9 CCD stereo camera, high-rises razor-sharp eyes, KSIS's color vision, and the ultraviolet and infrared detectors of MAVEN and Tianwen-1, all brought to bear on a visitor from another star. For the first time, a planetary fleet is close enough to capture data that ground-based telescopes could only dream of. The universe has handed over a riddle, and every instrument is now aimed at unraveling it. The question is no longer just what Atlas is, but how such an object could appear at all. The numbers say it shouldn't be here, yet every signal confirms it is. Survey models fail to explain the sequence: a skyscraper, a mountain, then a colossus. Each new detection forces scientists to redraw the map of what's possible. And as Atlas races through the inner solar system, the statistical shock lingers, demanding answers. The next step, understanding how Mars's unique vantage point turns this improbable encounter into an unprecedented scientific opportunity. Mars sits just 30 million kilometers from Atlas, a vantage point that rewrites the rules of observation. Earth, by contrast, stares across a gulf 9 times wider, nearly 270 million kilometers, where even the most powerful telescopes struggle to resolve more than a shifting speck. At this distance, Mars-based instruments are not just closer. They're orders of magnitude more sensitive to subtle changes in brightness, color, and trajectory. But proximity is only the first advantage. Atlas is tearing through space at 44 kilometers per second, crossing the distance between Mars and itself in less than a week. For Mars orbiters, this means every minute counts. Commands sent from Earth to Mars take 14 minutes to arrive, and another 14 minutes for confirmation to return. There's no room for last-second adjustments. Every maneuver, every exposure must be planned and uploaded days in advance. The fleet's window to capture Atlas is brutally short. In 72 hours, the comet will slip behind the Sun from Mars's perspective, vanishing into radio silence. After that, no signal, no data. Just the slow wait for Mars to re-emerge weeks later. The geometry of the encounter pushes every system to its limit. Mars Express, HiRISE, Cassis, and the rest must synchronize their orbits, instruments, and data streams to catch fleeting photons from a target racing across the Martian sky. At 30 million kilometers, even the sharpest cameras reduce Atlas to a point source, hundreds of times smaller than the smallest Martian crater they were built to study. Yet by stacking exposures, tracking the comet's motion, and leveraging Mars's unique position, scientists can extract brightness curves, spectral fingerprints, and, if the coma flares, hints of structure that ground-based observers can only dream of. Every calculation, every command, is a BET against time and distance. The team has 72 hours before Atlas disappears behind the Sun, taking its secrets with it. The numbers are unforgiving. One chance, one window, and a cosmic visitor that will never pass this way again. A comet this large should be impossible to miss, and yet, by every measure that matters, Atlas acts like it wants to disappear. 33 billion tons of interstellar ice and rock, tearing past Mars at 44 kilometers per second. And still the outflow barely registers. Standard models say a body this size, swept by sunlight at this distance, should vent gas and dust in torrents. The numbers don't lie. A typical comet of this mass, heated by the Sun, would lose hundreds of kilograms every second, its jets carving the orbit with each outburst. But the Mars fleet records something else. Dust production hovers below 4 kilograms per second. Spectrometers, Omega, Nomad, MAVEN's ultraviolet suite, strain to find any sign of water or carbon dioxide. The expected signatures, those bright emission bands, are missing or buried in noise. The paradox deepens with every orbit. If Atlas is shedding so little mass, why does its coma remain so faint, its tail so subdued? The physics of cometary motion is built on the rocket effect. As volatile ice sublimates, it jets from the surface, pushing the nucleus in the opposite direction. The result, for every active comet, is a measurable nudge, a non-gravitational acceleration that shifts the orbit, sometimes by tens of meters per day squared. But Atlas, for all its bulk, drifts along a path set by gravity alone. Mars-based astrometry, refined to fractions of an arc-second, finds no deviation. Less than 15 meters per day squared, well inside the error bars, indistinguishable from zero. Even the ratios refuse to cooperate. In the solar system, water vapor dominates comet outflow, with carbon dioxide a distant second. The expected ratio is 8:1, water to carbon dioxide. But preliminary spectra from Webb, confirmed by Mars Express, hint at the reverse. If any gas is present, carbon dioxide outpaces water 8-fold. The chemistry is upside down. The rocket effect, the very mechanism that should betray Atlas's activity, is absent. This is not just a faint comet. It's a challenge to the underlying physics, the largest interstellar visitor yet found, passing closer to a planetary fleet than any before, and still, the basic forces that should drive its evolution are missing in action. Scientists are left with a puzzle, a mass that shouldn't be here, an outflow that won't appear, and an acceleration that refuses to materialize. Each missing piece calls into question the rules that have governed cometary science for generations. The instruments now turn to the details, spectrometers and imagers straining for any anomaly, any clue that might explain the silence. The answers, if they come, will be buried in the spectra, waiting for someone to notice what's not there. Spectrometers become the backbone of this campaign. Their task simple in theory and punishing in practice. Extract the chemistry of an interstellar visitor from a signal just above the noise floor. Omega, riding aboard Mars Express, splits every photon into 350 distinct channels, each one tuned to a narrow slice of the visible and near-infrared. The result? Spectral cubes that can expose the faintest hint of carbon dioxide, water ice, or organic molecules, if they exist. But with Atlas 30 million kilometers out, even a giant yields little more than a whisper. The spectrometer's detectors, optimized for Martian frost and dust, now search for alien fingerprints in a haze where every electron counts. Nomad, mounted on the trace gas orbiter, pushes sensitivity further. Its sensors can register gases at parts per trillion levels, a feat designed for sniffing methane above the Martian plains. Here, that sensitivity is repurposed. Any spike in the ultraviolet or infrared could betray a volatile outburst, a brief window into the comet's true composition. But the challenge is relentless. The comet's coma, unresolved by any camera, becomes a moving target for spectrometers that must catch fleeting emissions as the nucleus races across the Martian sky. Orbit dynamics add another layer of complexity. Mars Express loops the planet every 6.7 hours, tracing a wide ellipse from 300 to 10,000 kilometers above the surface. The trace gas orbiter completes a tighter circuit every 2 hours at a steady 400 kilometers altitude. Mars Reconnaissance Orbiter, with its high-rise camera and CRISM spectrometer, flies a brisk 112-minute path. These mismatched orbits mean that no single instrument can keep Atlas in sight for long. Instead, each pass becomes a carefully scheduled handoff, a relay race dictated by celestial mechanics and the comet's relentless pace. Bandwidth sets the final limit. Each orbiter can downlink roughly 200 megabits per minute, enough for a handful of high-resolution images, or a few compressed spectra per orbit. But with Atlas visible for just 72 hours before solar blackout, and Mars itself spinning beneath the fleet, every bit must count. Teams prioritize spectral data over imagery, compressing files, stacking exposures, and triaging downlink cues to ensure nothing essential is lost to the noise of Martian dust or the silence of solar conjunction. Behind the numbers lies a choreography of commands. Ground teams upload observation sequences days ahead, targeting precise windows when the comet aligns with instrument fields of view. There are no second chances. Each orbit, each exposure, is a bet against time, distance, and the hard ceiling of telemetry. The campaign becomes a study in adaptation. Martian spacecraft, designed for a planet, pressed into service as interstellar sentinels. The data, once captured, will take months to process and interpret. But for now, the only certainty is the urgency. Extract every possible clue before Atlas vanishes behind the sun and the trail goes cold. October 1st. In control rooms from Pasadena to Darmstadt, every monitor glows with countdown clocks. The window for uploading observation commands is shrinking by the hour. Mars orbiters, built for a planet, are about to gamble everything on a target that won't wait. Engineers review the final command blocks. Each line of code must steer instruments with split-second precision, catching a comet that crosses a third of the Martian sky in a single orbit. There's no room for error. Every sequence is checked, then checked again, before the final uplink. The one-way light time, 14 minutes, means that by the time a signal arrives, the comet has already moved thousands of kilometers. Martian weather adds another layer of uncertainty. Dust season is in full swing. Atmospheric models show optical depth, tau, hovering between 0.7 and 1.2, enough to mute sunlight, scatter photons, and bury the faintest signals in noise. A spike in tau could erase the comet from view, making every exposure a race against the next dust surge. Teams monitor live feeds from Marcy and Tianwen-1's meteorological suite, searching for the first hint of a regional storm. No global event yet, but local spikes could force last-minute adjustments, longer integrations, higher dynamic range, or, if the dust thickens, canceled exposures. The choreography is relentless. ESA's Berlin and Paris teams coordinate calibration for HRSC and Omega, while JPL's engineers in Pasadena finalize high-rise slews. In Boulder, MAVEN's science leads track ultraviolet windows, cross-checking with dust forecasts. CNSA's Tianwen-1 team, linked by secure channel, confirms their own command upload. Each agency, each instrument, must act on a schedule set not by human preference, but by orbital mechanics and Martian weather. There are no second chances. Once the upload window closes, the orbiters are committed. In less than 2 days, 6 spacecraft will aim their sensors at a point in the sky where, if the dust holds and the timing is perfect, the largest interstellar object ever detected will flicker into view, briefly, and perhaps for the last time. Solar activity hovers over every calculation. Mission planners, already working against Martian dust and a shrinking observation window, now track the sun's mood with near-religious intensity. Even a moderate coronal mass ejection, CME, could scramble signals, blind sensors, or force spacecraft into safe mode, erasing days of preparation in a single burst. Space weather teams at NASA, ESA, and CNSA scan real-time feeds from the Solar and Heliospheric Observatory, searching for the first spike in proton flux. As of October 1st, the sun holds steady. No major CME alerts, nothing aimed at Mars. But the warning remains pinned to every mission console. If the sun flares, the fleet goes dark. Yet the greater threat isn't a sudden storm, but the geometry of the solar system itself. On October 29th, Mars slips behind the sun as seen from Earth, a hard blackout enforced by physics. For 6 weeks, every orbiter and lander falls silent. Commands can't reach Mars. Data can't return home. Engineers call it solar conjunction, but to the science teams, it's exile. Any observation not captured and downlinked before the cutoff is lost, potentially forever. The Mars fleet's encounter with Atlas unfolds under this ticking clock, a planetary alignment that turns a rare opportunity into a race against the void. Contingency plans run deep. Each orbiter carries pre-programmed safing routines, ready to hunker down if a solar event strikes. Data pipelines prioritize the rarest frames for transmission, shuffling bandwidth to protect the most valuable spectra. In the control rooms, mission leads rehearse blackout protocols. What to save, what to sacrifice, who calls the shot if the sun misbehaves. The risk isn't just technical, it's existential. If Atlas flares, fragments, or shifts course while Mars is hidden, the evidence could vanish into the sun's glare, beyond reach until December. The campaign's outcome depends not only on engineering, but on the whims of a star 150 million kilometers away. The silence, when it comes, will be total. And when the fleet re-emerges, the story of Atlas, whatever happened in those lost weeks, may be written in gaps as much as in data. Mars Express delivers its first images, a faint, elongated blur, stretched 20 kilometers end to end, with a width just over half that. No comet in the catalogs matches these proportions. Even at 150 meters per pixel, the nucleus remains unresolved, a streak of reflected sunlight tumbling across the sensor. Yet the brightness curve, sampled every 8 minutes, sketches a rhythm. Atlas spins once every 8.3 hours, but not smoothly. Photometric dips and surges betray a tumbling rotation as if the object can't settle on a single axis. Colin Wilson, lead scientist for Mars Express, describes the scene in clipped, careful language. The light curve amplitude, how much the brightness swings in one rotation, suggests a body far from spherical. Atlas is no icy snowball. Its silhouette, stretched and uneven, hints at a battered past, a relic shaped by impacts, tides, or perhaps the violence of ejection from another star's domain. High-Rise and Cassis, working at the edge of their limits, contribute only confirmation. The nucleus is too small and too distant for their optics, but the coma's faint glow matches the Mars Express data point for point. Cassis's color channels, stacked and aligned, reveal a surface albedo of just 0.04 to 0.06, a darkness rivaling the blackest asteroids, far less reflective than any known comet. Every instrument, every exposure, converges on the same conclusion. Atlas is immense, dark, and spinning in a way that defies simple models. No jets or fans show up in the images, just a steady, slow roll, punctuated by the occasional flicker as sunlight catches a crater or ridge. The shape, the rotation, the albedo, they all point to a history written in collisions and cosmic exile. But the images, for all their detail, stop short of revealing the heart of the mystery. The surface is a cipher. No obvious vents, no bright patches, no clues to the chemistry lurking beneath. The instruments now pivot, turning from form to substance. Spectrometers prime for the next round, searching for the fingerprints of alien ice and dust in the faintest glimmers of light. Spectral data from Omega and Nomad arrive in fragments, each one a clue to a chemistry that refuses to fit expectations. Across hundreds of channels, carbon dioxide dominates. Its signature 8 times stronger than water. In every known comet, water leads and carbon dioxide follows. Here, the order is reversed. If these numbers hold, Atlas is rewriting the rules of comet formation, challenging the basic assumptions that have guided planetary science for decades. The coma's faintness only sharpens the puzzle. With a mass between 28 and 38 billion tons, even the weakest sunlight should drive outgassing visible from Earth. Instead, the gas is barely detectable, dust output is minimal, and the classic rocket effect, the non-gravitational push that bends every active comet's path, is missing. Astrometric data from Mars Express and TGO confirm it. Atlas's trajectory is a straight line, deviating by less than 0.03 degrees after the Mars flyby. No measurable thrust, no sudden veer, just the relentless pull of gravity. The numbers don't add up. A body this large, this close, should be carving a visible arc across the sky. Instead, Atlas tracks as if inert, a mountain of ice and rock untouched by solar heat. Dynamical models strain to explain it. Standard comet physics predicts that even a modest outflow, driven by carbon dioxide or water, should nudge the orbit, especially at this proximity to the Sun and Mars. Yet with every new dataset, the absence of acceleration becomes more pronounced. The only way to reconcile the mass and the silence is to invoke densities or structures outside the range of known comets, or to imagine a geometry so symmetric that every jet cancels its neighbor, leaving the nucleus motionless. Avi Loeb, Harvard astrophysicist and veteran of interstellar debates, steps into the uncertainty. He points to the mounting anomalies, the reversed chemistry, the missing acceleration, the statistical unlikelihood of finding a giant first. Loeb asks whether Atlas could be more than a natural wanderer, perhaps a fragment of alien technology, or a probe engineered to minimize its signature. Most scientists remain cautious, favoring extreme but natural explanations. But the data refuses to settle. Each new measurement sharpens the paradox, mysterios, a mass that shouldn't be here, chemistry that doesn't fit, and a trajectory that ignores the physics of every comet before it. The final numbers: carbon dioxide-dominated spectra, a refined mass in the tens of billions of tons, a path shifted by barely a hair, feed into the next round of models. Somewhere in the noise and ratios, the answer waits. For now, chemistry and dynamics raise more questions than they answer, leaving the story paused on the edge of discovery, the meaning still out of reach. Capture is rarely considered in interstellar science, but as Atlas moves through the Martian corridor, theorists confront a possibility. Could an object from another star become trapped by our sun? The answer depends on the existence of a keyhole, a narrow region in space, sometimes just 600 meters wide, where gravity can alter a comet's path enough to bind it. For Atlas, dynamical simulations focus on this corridor. Miss it, and the comet vanishes into interstellar darkness. Hit it, and Atlas's orbit could shift, perhaps even leading to capture. The physics are unforgiving. Atlas must lose nearly 8 kilometers per second of velocity to be caught, a change no natural process has ever achieved at this scale. Gravity alone falls short. The required momentum transfer is so precise that even the boldest models put the odds at less than 1 in a billion. Still, the debate persists. Some theorists point to radiation pressure, the constant faint push of sunlight on dust and ice. Over millions of kilometers, this can nudge a comet's trajectory by fractions of a degree. For Atlas, the effect is tiny, but in a scenario as delicate as a keyhole passage, even the smallest force could tip the balance between escape and capture. Others consider non-gravitational effects, asymmetric jets, sudden outbursts, or the release of gas beneath the surface. Yet Atlas shows no sign of these. There are no jets, no shifting path, no evidence of the classic rocket effect. The comet travels as if untouched, immune to the forces that have altered every other visitor. This absence leaves two possibilities. Either Atlas is the most perfectly balanced natural object ever seen, or something else is at play. Avi Loeb, known for challenging consensus, offers another explanation. If Atlas is artificial, designed to minimize its signature, then its lack of acceleration, its precise trajectory, and the statistical improbability of its discovery become intentional. The 600-meter keyhole is not a coincidence but a target. The required delta V, the absence of outgassing, the reversed chemistry, all become clues in a puzzle that stretches across the stars. December will bring answers. As Atlas emerges from behind the sun, telescopes will watch for shifts in orbit, changes in spin, or sudden brightening. If Atlas bends into a new path, even briefly, the implications will reach far beyond this single encounter. December brings the test. As Mars and Earth swing out of conjunction, telescopes across the globe and in orbit will search for the first sign of Atlas re-emerging from the sun's glare. The waiting is not passive. Teams have spent weeks refining prediction models, recalibrating detectors, and scheduling observation blocks to catch even the faintest flicker. Every asset with a clear line of sight, from ground-based observatories to the James Webb Space Telescope, stands ready to track changes in brightness, spin, or direction. The goal: verify whether Atlas's orbit remains unchanged, or if the data hint at a subtle, history-altering capture. Trajectory analysis becomes the arbiter. If Atlas's path curves, even by fractions of a degree, the implications ripple through planetary science. A captured orbit would challenge every assumption about interstellar objects and the sun's gravitational reach. Yet even a near miss, a brush past the so-called keyhole, would trigger a flurry of recalculations, forcing scientists to revisit models of solar system dynamics, outgassing physics, and radiation pressure. The precision required is daunting. The margin for error, razor thin. Each new data point carries the weight of rewriting textbooks. But the December campaign is more than a test of models. It is a rehearsal for the future. The European Space Agency's Comet Interceptor, scheduled for launch in 2029, draws its protocols from the lessons of Atlas, the mission's very premise: a spacecraft waiting in deep space, ready to intercept the next interstellar visitor, owes its urgency to the surprises and near misses of this encounter. The diversity of compositions seen across Oumuamua, Borisov, and now Atlas, rock, water, carbon dioxide, demands flexibility, rapid response, and a willingness to adapt on the fly. Each object is a messenger from a different corner of the galaxy, carrying clues to planetary formation, stellar evolution, and perhaps even the seeds of life. For now, the final answers remain hidden behind the sun. The December emergence will decide whether Atlas escapes forever or lingers in the solar system, whether its surface has changed, brightened, or fragmented, and whether its chemistry still defies explanation. The world watches, knowing that the outcome will shape how we search, what we expect, and how we prepare for the next cosmic visitor. If Atlas's course shifts, if its activity proves unnatural, if the data refuse to fit, then every model is up for revision. The Mars fleet's data, locked in memory until the blackout lifts, may hold the key. The story of Atlas is not yet finished. December decides what comes next. On October 3, 2025, 6 Mars orbiters captured the closest images ever taken of an interstellar object, 3I/Atlas, at just 30 million kilometers, 9 times closer than any Earth-based observation. These missions recorded detailed morphology, unexpected carbon dioxide dominance, and a mass of up to 38 billion tons, yet found no measurable acceleration from outgassing. Official data from the European Space Agency and NASA confirm that Atlas's structure, chemistry, and trajectory challenge current comet models. However, major questions remain: the exact mechanism behind its stable path, and whether organic compounds detected by NOMAD are primordial or altered in transit. With a 6-week blackout as Atlas vanishes behind the sun, the scientific community awaits its December reappearance to test trajectory predictions and refine formation theories. The Mars campaign has set a new standard for interstellar object study, established international protocols, and forced a revision of search models. As of today, the Atlas Data Archive stands as the most detailed record of an interstellar visitor, and its full meaning is yet to be revealed.